which is opened. Let's look at what we calculated. First floor is an open structure. Okay, so first floor is an open structure. So the wind loading was calculated as a pressure load, which is going to be applied on the columns. So 0.613 VE square, then times the net pressure coefficient times the size effect coefficient. That will give total pressure load. To get the loading on the columns, you multiply this pressure load by the width of the column facing, that is normal to the windage area. So our columns are 230 by 230, so you multiply 1.91 by 230. 0.43. You know why? Like we said, if you look at that in this direction, these are the columns. Once the wind pressure is coming there, the wind loads on the columns in this open structure will be the wind pressure times the cross-sectional area times the projected area of the columns. The wind pressure times the projected area, and that projected area is, in this instance, the width of the column, which is 0.23. So if you multiply 1.91 by 0.23, you then have 0.4393. So we do that, add member load 0.4393. What direction is in the Z direction? So change it to global Z. Add. So we'll select these columns from the foundation level to the ground floor. Select them. That side. Wow. So that's great. Great. So this is wind load in the Z direction. The next thing to do is to do the wind load in the X direction. We have calculated that as well too. Let's go to the roof level and see. Good. This is the X direction, the shorter side. The joint loads per joint is 7.051. Let's go quickly. So this, let's look at the, so this is the, and then this is the X. 7.051. So let's select the X direction. Let's select that region. Then you view selected object only. Great. So you have 3 joints. Let's look at. Yeah, that's good. 1, 2, 3. So 6 joints. So X direction, you add wind load 7.051, joint load. Make sure your direction is correct, so apply it in the global X. 7.051. Let me apply all at once. So this is between the second and the roof level. Let's go to between the third and fourth level. Let's look at between the second and third. Okay, between second and third is similar, 7.051. Oh, that's okay. That's nice. So the pressure intensity did not vary significantly because of the height. So the wind pressure is significantly height dependent, and it starts changing significantly when the height is greater than 10 meters, because the reference elevation for the wind velocity is at 10 meters. So we also have the wind force calculated to be similar, and this is 7.051. So we're going to apply this wind force 7.051 on these nodes between the first floor and then the roof level. Great. Then on the first floor level, because it's opened, the wind pressure on the open structure on the first floor level is on this area. So we have it to be 1.91. So 1.91 times the projected area of the columns will give us the wind load. So 1.91 times 0.23 will give us 0.4393. which is the wind load on the columns. Note again that it's in the x direction, so change this to x direction and say add. Once you select your columns, you assign to selected beams, and then it has added your loads. Okay, so these are your wind load in the x direction, and then we have the wind load in the z direction. Great. Note that you can also use STAAD's internal wind load generator in compliance with, if you're designing a structure for a client in line with ASCE 7. If you're analyzing structures in the petrochemical industry or the oil industry, for some clients, in line with ASCE 7, which is the American Code of Practice for wind load generation, STAAD can internally calculate the wind pressure intensities and the associated wind load using wind definition. But we decided to calculate this manually so that the understanding is well comprehended. So the next thing for us to do is to calculate our load combination in compliance with the code of practice.